So we're looking at proving, actually deriving an equation for electrical potential due to a point charge. So first let's understand electrical potential again. It's nothing but work done on a unit charge carrying from infinity to point A, right? That's your electrical potential. Now, the thing is, the electrical field that is produced by a point charge, by a cylindrical charge, a wire, so on and so forth, they are not the same. Infinitely big plate, we have done all of this derivation. They're not the same. So we have to go case by case, and we need to understand that the electrical potential by different structure is different. So we are starting off with the smallest possible or the easiest scenario actually, and that is your point charge. A quick question for you guys. Here in this heading, what is the point charge? What is it? Is it the source charge or test charge? Yes, it is the source charge. The source charge itself is just a dot. The final answer over here looks like this: K times of Q divided by R, where Q is your correct source charge. And what is R? Distance from the source charge. That's all. It's a very simple expression. Source charge. Okay, guys. Now, this is your actual derivation. So we are considering a charge which is Q and it's at the origin. And we are considering a point A which is R units away. Now we are trying to figure out a charge which is at infinity, say Q naught, with charge Q naught. It's being carried from infinity to point A. Now, how do we do it? So we have to make use of the funda. What's funda? Along this path, we'll take a point P, and from point P to point Q, say the distance is very small and it's represented by dx. And this point P is at a distance of x units away from the origin. And the work done over here is dw. So by figuring out the work done for the small length, and we're looking at the similar pattern over here because it's a point charge and so on and so forth, we will be able to add all the work and thus get the entire work. That's the whole funda, is it not? So let me put it this way: work done on Q naught to displace it by a length of dx is what? Is nothing but dw is equal to a dot product between the field strength at that point and the displacement. And when we remove the dot product, we end up with cos of theta. And what is theta over here? You guys have to be telling this. What is theta over here? Here theta is 90 degree, is it not? Nope, it is 180 degree. Why is that? As the displacement and the electrical field are opposite of each other, that is, they are anti-parallel. My bad, anti-parallel. Anti-parallel. Agree? And so this will be nothing but this is the smallest possible work that we can figure out. Now, what is the total work then? Well, we need to add all the work, right? And moving Q naught from infinity to point A, which is R units away. So how do you do that? We need to add all the work by moving from infinity to point A, while moving from infinity to point A. And this is nothing but minus of infinity to point distance R and dx. Agree? So I hope you guys understand why the limit values are changing, because we are trying to express in terms of, yes, length, distance away, dx, is it not? So let's figure out the rest of it. So of course, force will not remain the same. This is not a point charge does not create a uniform electrical field. So this changes as per this formula, square of the distance, right? In this case, I'll take it as x square. And so we have minus k q naught, all these are constant, infinity to r dx by x square. So what is the integration of this? Minus 1 by x. So and the limits will change from infinity to point or length r. So negative of negative is positive, q naught by x square, sorry, x. So in this case, it will be 1 by r minus 1 by infinity, which is 0, and you have your final expression as q naught by r. So next thing is, for a unit charge, work will be what? Why is that we are doing this? Yes, that's the definition of your electric potential, right? And so we have to figure out it for a unit charge, not q naught. What we found now is electrical potential energy, right? So for unit charge, it will be what? It will be W by Q naught, and that's nothing but your potential at point A. And here the source is your source charge, is your point charge. Point charge. Again, you don't have to represent all of this. It's just VA, but I'm just writing it. KQ by R. That's it. Very simple, is it not? So what is that we are seeing over here? Let's analyze the formula. A point charge generates dash symmetrical electrical potential. And how do we come to this conclusion? You need to answer both. Yes, it is correct, cylindrical. Right, is it not? It's something like this. Nope. It's common sense that it has to be spherical. Forget about the formula, it has to be this. Like sun is radiating out and so on and so forth. Right, similar to that, how sun is radiating out the light. Similarly, we have this a point charge radiating out field, or altering the space in that way, so on and so forth. So it has to be what? Yes, it has to be spherical. But how can we come to this conclusion looking at the formula? Because it is proportional to 1 by r. Potential is proportional to 1 by r. Right? Because of that, we will be able to come to this conclusion. Now, the potential at infinity as per the formula, what will that be? All you have to do is substitute r as infinity. So 1 by infinity is 0. So v is equal to k q by infinity. So this is 0. So v is inversely proportional to the length, the distance, right? In terms of a graph, how does this look like? So this is your distance, that's your electric potential. So distance and electrical potential, x and y axis. So when you draw this graph, you'll end up something like this actually. Yes, so not a ideal thing. So say this is 1 unit away. So this will be something. Depends on the charge actually. Just a second. Oh, my battery is getting over. Okay, guys. So here it's one unit. I won't be able to write though. Yeah, this is, please make a note that this is 1 unit. And before that, the value, anything divided by a value which is less than 1, will have a value which is more than 1 per se. It actually depends on unit charge and test charge, source charge, my bad. Sorry, okay, I want to tell 1 point, so I kind of, so this, after 1, the value will keep reducing and so on and so forth. Anyways, let me come back to this. The graph, I'll try to do it some other point because now the battery is not working. My device has stopped working. So what is that we looked at? See, we know that charges produce electrical field. That is, they alter the space around it so that there is a certain force that another charge will experience. We're trying to understand with the help of a scalar quantity known as electric potential. Electrical potential at a point is nothing but the work that we need to move a unit positive charge from infinity to that point. And we know that electrical field by different charges, different patterns, different configuration, they alter the space in a different way. Not everything is radiating out. Not everything is reducing at the rate of 1 by r. It differs, right? So it differs depending on how things are distributed, the charges are distributed. In this case, we are considering a simple scenario of point charge. So we have a point charge at origin. We are trying to figure out the electrical potential at a random point, which is r units away. So we are taking up a charge q naught from infinity and moving it to point A. Say along the path, we have a point P and P to Q. Actually, this should be capital Q. Don't get confused, guys. This is not a charge. This is capital Q. So we have a length of, say, dr, and the work done in moving the charge from point P to, say, a small length dr is dw. So what is that we are trying to do? We are trying to figure out, okay, how much work am I doing in this small path? So once I do that, I can figure out the path for the entire length by just adding them up. And fancy way of adding things is we can do that with the help of integration, and we did the integration. And a small set of observation that we can make from this result. One is that it has to be spherical in shape. Okay. And we'll be looking at this point actually, something called as equipotential surface and all of that. And that at infinity, the unit test charge has no influence. So when you plot a graph of distance versus, or in this case, electrostatic potential versus distance, you get a graph like this. Okay. So I try to make a point over here, but anyways. So now it's time for you guys to pause and have a look.